We have seen in our earlier discussion that when a magnet is brought near another magnet, there is some sort of an influence. We also saw that earlier it was found out through various experiments that a magnet has a certain property of influencing other objects. Now, this influence is exerted by a magnet without any direct contact or without touching the other object. As you saw in our previous lecture, if you recall, a North Pole and North Pole repel one another without touching. A North Pole and a South Pole attract one another without initially touching. So how do you think without touching they are able to influence? Now let us consider a simple analogy. Over here in the pool, I have placed two balls, as you can see. Now one of the balls is connected with a string and the other end of the string is held in my hand. Now I apply a certain jerking motion to this particular ball held with a string. As you can see, some sort of disturbance travels in the outward direction and the other ball, that is the orange one, gets disturbed. Now obviously, as you can see, there is no direct contact in between the green ball and the orange ball. Yet when I am applying a jerking motion on this particular ball connected with a string, the other ball is getting disturbed. A similar thing happens in case of magnets. When a particular magnet is brought near another magnet or a particular substance, it has some sort of a disturbance around it. This disturbance, with the help of which it influences other magnets or other objects, is known as the magnetic field. So let us see how we can define a magnetic field. The space surrounding a magnet within which the magnet has its influence is known as the magnetic field. So it is defined as the space surrounding a magnet where the magnet can influence another object with a certain force. So inside the magnetic field, the magnet can apply a certain force either to repel or to attract. Now consider the same analogy with a slight twist. Over here I have again kept these two balls and another ball quite far away from the green ball. Now you will notice that when with the string in my hand I am applying a jerking motion, the ball that is near to the particular ball, this is the green ball, that ball is getting shaken up vigorously. But the ball that is far away, that is the orange ball, that is farther away from the green ball, is not reacting as vigorously. Now why is this so? As you can see, the disturbance that I am creating with the help of this green ball is affecting the ball nearer to it more because it is closer. But the ball that is far away is not as affected by the jerking motion of the green ball because, as I told you, it is much far away. So a similar thing happens in case of magnets as well. What happens is when a magnet is brought near a particular object or another magnet, its ability to influence the other substance increases if the distance is less and decreases if the distance is more. Now this animation will make it clear to you. You will notice that when a magnet is brought near these pins, the closer ones get attracted at first, but the ones that are farther away are not attracted. Why? Because when the magnet is being brought in here, these are close, whereas the other ones are far away. So we can say that the magnetic field depends on distance. Greater the distance, lesser is the ability of the magnetic field to influence the objects. So it was only when the magnet was moved closer did those pins get attracted to the magnet. So now let us see a video whereby we will be able to demonstrate that magnetic field or the influence of the magnet indeed depends on the distance. If you see this video closely, you will find that a magnet over here is being brought close to this particular needle. Now you will notice that when the magnet is brought close to the needle is starting to shake vigorously. The moment the magnet is being withdrawn, the vigor of the needle with which it is shaking is decreasing. And this process is being repeated and a similar result is found. The moment the magnet goes near the needle, you will find that the needle becomes absolutely taut and it points absolutely in the direction of the magnet and the shaking becomes vigorous. But when taken away, the needle becomes kind of loose and the shaking is less vigorous. Now we will look at another video to find out what the pattern of magnetic field is around a magnet. Now in this video, you will find that a magnet in the shape of a bar has been considered. In this picture, as you can see, the magnet has been marked out as North Pole by the red end and South Pole by the blue end. Now we perform a very simple experiment to determine the pattern of magnetic field around this bar magnet. Now what we do is we place certain iron filings around the bar magnet. Once we place these iron filings around the bar magnet, we will find that their arrangement around the magnet is not haphazard or random. If you look closely, you will find that they are arranged in a particular pattern around the bar magnet. The iron filings are very densely arranged at either end of the magnet and somewhat sparsely arranged in the central portion of the magnet. So as you can see, we are getting the pattern of the iron filings clearly, and this indicates the pattern of the magnetic field around the magnet. So now we are going to look at another video which tells us that this magnetic field is not only a 2D phenomenon, it is a 3-dimensional phenomenon. In this video, we have considered a block which has liquid in it and the iron filings are suspended in the liquid. Now notice what happens when the bar magnet is pushed inside. You will find that these iron filings which were suspended are no longer randomly suspended. They are arranging themselves around the bar magnet in a manner that indicates the magnetic field lines of this particular bar magnet. Again, as you see, they are dense at either end and less dense at the center. So with the help of this very simple experiment, we have been able to demonstrate that magnetic field lines are present not only in 2D space but also in 3-dimensional space around the magnet, and the pattern is as given by these iron filings. So we have seen that the bar magnet makes the iron filings arrange themselves in this sort of a pattern, and the concept of this pattern was first proposed by William Gilbert back in 1600 when he conducted various experiments on magnets. Now William Gilbert had proposed that the magnetic field, or this pattern of the magnetic field, be depicted by magnetic field lines. They are depicted through magnetic field lines. So as you can see over here, the magnetic field lines are showing the pattern of the magnetic field. If you look closely, you will find that over here they are dense, whereas not so much in this region. So experimentally it has been found out that magnetic field lines start from the North Pole, or they are generated at the North Pole. In other words, we can say that magnetic field is generated at the North Pole, and outside the magnet they travel from the North Pole all the way to the South Pole. So as you can see, magnetic field lines are directed from the North Pole to the South Pole outside the magnet, and at the South Pole magnetic field lines are entering the magnet. Now what do you think happens to the magnetic field lines once they enter the South Pole? To know this, we go inside the magnet. Now as you can see, inside the magnet the exact opposite thing happens. Over here the magnetic field lines travel from the South Pole to the North Pole. Now as you can see, this ensures that the magnetic field lines are continuous, that there is no breakage, because they start at the North Pole and go all the way to the South Pole outside the magnet, and once inside they move from the South Pole to the North Pole. Now let us see, with the help of an experiment, a very simple one, how we can find out the direction of magnetic field lines and map them. Now, in order to perform the experiment, we consider a simple compass. Now, the compass, as you can see, is housed in an aluminium case. On the face of the compass, the directions have been marked, and the key feature of a compass is it contains a magnetic needle. Now, one end of the magnetic needle, as you can see, has been marked with red. This red portion indicates the north pole of the magnetic needle because it always points towards the south pole whenever kept near that particular magnet. So let us see how, with the help of a compass, we can plot or map the field lines. Now we start from the north pole. As you can see, when the compass is kept near the north pole, the red part of the compass or the needle of the compass is facing away from the north pole. Why? Because the red part of the needle indicates the north pole of the magnet of the compass. And since like poles repel, it is facing away. Now let us see what happens when we place this compass at different points. Now I have placed the compass, let's say, at this point and this point. Now when I have placed it at this point, if the north pole repels the north pole, then don't you think that the direction of the needle should have been in this point? But such is not the case. So we can say that the needle is not just being repelled by the north pole, it is indeed facing away from the magnetic field. Or in other words, the field lines are moving from this direction all the way to this direction, that is from north to south. So we can say that the needle is pointing in the direction in which the field lines are moving, or away from the direction of the field lines. So if I place it at any other point, we will find that the needle deflection remains in the direction where the field lines are going, or it is being repelled by the magnetic field, we can say. So in this way, if we place the needle at various points, that is the compass at various points, we will find that the direction as pointed out by the magnetic needle gives us the direction of the magnetic field. So this is how, with the help of this very simple experiment, we are able to plot or map the magnetic field lines around any given magnet. So how can we now define magnetic field lines? Magnetic field lines in a magnetic field are those lines along which the north pole of a magnet will move if free to do so. So over here we found that when we place the compass, the north pole moved freely because it aligned itself in a direction as to show us the direction of the magnetic field lines. Magnetic field line direction is given by the direction in which the north pole will point. So over here, the north pole is pointing in this direction. So the direction of the pointing of north pole gives us the direction of magnetic field lines. Now let us consider the bar magnet and the field lines at either ends. I previously mentioned to you that the field lines are highly crowded at the ends and separated or sparse at the center. Now what does this mean? This means, as you saw in the previous video, the interaction at the ends is much more than the interaction at the center. In our previous video we saw that the iron filings were highly crowded at the ends because the magnet was influencing them more. But at the center, where the field lines are separated, the iron filings were interacting less with the magnet. So we can say more crowded the field lines, more is the interaction. Less crowded the field lines, less is the interaction. Now notice what happens when two magnets are placed face to face or end to end with opposite poles. Now since opposite poles attract, they will have a strong influence. Now when these two poles are brought closer, you can see that the field lines are highly crowded at this end. However, if you consider the centers of either magnet, you will find that the field lines are pretty much separated and sparse. Even at the extreme ends of both the magnets, the field lines are not as crowded as they are in the central region. So it means that whenever an object is placed in this region, the influence will be much more than anywhere else. So what does this imply? This implies that strength of magnetic force, that is the ability of a magnet to influence any other object, is inversely proportional to the distance in between field lines. So if the distance in between field lines is more, from this relation we can say that strength of magnetic force is less, as influence will be less. Similarly, if distance between field lines is less, or in other words, if the field lines are highly crowded, then from this relation we can say that the strength of magnetic force is more because its ability to influence the object will be much more. Let us now take a look at a video in order to understand more about the properties of magnetic field lines. Over here you will find that the magnetic field lines will be plotted in a similar manner. That is by keeping compasses at various points and plotting the direction in which the needle points. Now there is something intriguing and interesting about the magnetic field lines to note. Now take a look at a similar experiment carefully. Over here, a piece of cork is studded with a nail, and as you can see, the magnet attracts this because of the nail. Now notice what happens if various positions of this nail are considered. You will find that the magnetic field lines come very close to one another and almost touch and get dense, but they never intersect one another. So we've studied a lot about magnetic field lines. Now let us see how we can plot the magnetic field lines of the Earth. Now back in 1600 AD, William Gilbert had proposed that the Earth behaves like a huge magnet. So obviously if the Earth is a huge magnet, it must also be having magnetic field lines of its own. So let us see how we can plot the magnetic field lines for the Earth. Magnetic properties of the Earth is due to the fact that it contains molten iron at its core. It contains molten iron at its core, and this gives rise to the magnetic properties. Now in a similar manner, we place a compass needle which contains a magnet inside it at various places, as you can see, in outer space. Now accordingly, as the needle is deflected due to the magnetic field of the Earth, we take the direction of magnetic field lines to be in that particular direction, because we have seen that the compass needle always points away from the magnetic field. In other words, it shows us the direction of the field lines. So if we proceed in this manner, we will find that the needle always points towards the geographic North Pole. That is the red part of the needle. And the silver part is always pointing towards the geographic South Pole. This means that at the geographic North Pole, the Earth must be having its magnetic south, and at the geographic South Pole, the Earth must be having its magnetic north. This is why with the help of a compass, we are able to navigate easily, because it tells us which direction the geographic north is. And as you can see over here, we have indicated the magnetic lines of force of the Earth, as we have found out with the help of a compass. Now the alignment of this particular magnet inside the Earth has a name to it. This alignment is known as the magnetic axis, because it has been found out through various experiments that this axis is along which the magnet is lying, and around this the lines are being formed. Now this axis is the rotation axis, or around which the Earth rotates. As you can see, the rotation axis does not coincide with the magnetic axis. And what does this tell us? This tells us that the geographic North Pole does not coincide with the magnetic south. and neither does the geographic south pole coincide with the magnetic north. There is a very slight deviation. So this must be kept in mind while navigating with the help of a compass. So let us study about the properties of magnetic field lines and recapitulate what we have learned so far. We have learned that they are closed and continuous curves, that there is no breakage in the magnetic field lines. Outside the magnet, they are directed from the north pole towards the south pole of the magnet. So if I consider a magnet like this, and if this is the north pole and this is the south pole, then outside the magnetic field lines will be directed in this manner. Similarly, because magnetic field lines are closed and continuous curves, inside the magnet they are directed from south pole to north pole. So again, let's say I consider the magnet, and this is north and this is south. Outside the magnet, as I mentioned, they are directed from the north pole to the south pole. So they are entering at the south pole. Now what happens once they enter the south pole? Since they are closed and continuous curves, they continue without any breakage. So as you can clearly see, inside the magnet, from south pole to north pole is the direction of the magnetic field lines. The field lines gives us the direction of the magnetic force. As you saw in the case of a compass needle, the red part of the needle was always deflected away from the magnetic field. Or in other words, it pointed in a direction as it would have pointed if there was a force acting on the red part. So this indicates that the field lines give us a direction of the magnetic force, because the compass needle points in that direction which is away from the magnetic force. The magnetic field lines never intersect one another, and we found this out with the help of a very simple experiment whose video I showed you. Magnetic field lines are crowded near the poles and separated near the middle of the magnet or far from the magnet. This is how we found out that the interaction of any substance is far more at the ends than at the center. Even if we take a magnet near a particular substance, the force or the influence will be more because the field lines will be more crowded near to it. But if we take the magnet far away, then the field lines will become less crowded and the force or influence will be less.